it's after lunch, so I'll go easy on this. I hope you have been enjoying the conference so far. So I work for KDAB, which is a Qt service partner, which means that as part of my daily duties, I also work on Qt itself. And during the last few months, few years, I've been working on a technology inside Qt, which is called Qt3D. Just pop quiz, how many of you are using Qt right now? Okay, some of you are. How many of you know about Qt? Yeah, okay. Well, I mean, at least I've heard the name, so you know that what it's about, I guess. So what I'm going to see today, I'm going to give you, as I said, a very gentle introduction to what is Qt3D, why we built it in the first place, what are its features, and basically how does it work in a generic fashion. The core of Qt3D is something called an entity component system, which I'm going to explain and spend some time on that, because it's basically what allows Qt3D to be so flexible and so powerful. Apart from that, then I'm going, of course, to tell you a little bit about how to draw something. This is Qt3D, as the name says, is a library to build 3D scenes. So I'm going to tell you a little bit about how to create geometries, how to transform those geometries, how to specify different materials and so on, lights inside your scene. A very gentle introduction. Don't be scared by the page numbers. They're very inflated because I got something like 200 extra backup slides in case some questions arises and I have a slide ready for me to explain something without me start drawing horrible diagrams over there. So I got the slides prepared for that. So a little bit about drawing. I got some extra slides about input handling. So apart from drawing inside a 3D scene, you of course want to interact with the 3D scene. So how can we do that inside Qt3D? And finally, I'd like to finish this talk a little bit about something that we call the frame graph. That is basically the way that you describe how a scene is rendered inside Qt3D. Qt3D does not bake any specific rendering algorithm. You're free to choose how to render your scene. So you're free to say, please render this, do a first pass in which you render certain things, do a second pass in which you render other things. It has basically a data-driven description of how the scene is rendered. This has many positive things in terms of having the maximum flexibility for you when it comes to, but I'd like to change defaults a little bit. I like to do something slightly different. You can do that. You have all the power. And then finally, I got very, very extra stuff in case, again, some questions arises, but I'm not hoping to get to that. So for those of you who don't know about Qt, just 2 minutes introduction of what Qt is. Qt is a C++ framework to build user interfaces, to build nice user interfaces. It has a very long story. It was released in 1994, which, by the way, is before the first C++ standard was released. Yeah, and this still affects today. And yeah, it's still alive. It has switched a few companies, so it has a very long history. So it's 23 years around now. And the fact that people are still using Qt, because fundamentally it's a C++ framework, which means you write native code, there is not an interpreter in the middle, and it's cross-platform. You can build your application on Windows, Linux, Mac, and recompile it for another platform, or even Android or iOS these days, and the application still works. You write your application once, and you move it elsewhere, and it just works. Yep. It's very successful. These days, it's actually an open source project, and it's developed by several companies. The blue one, the biggest one, is, of course, the owner of Qt, the Qt company. But if you look at the company stats, there are many, many things in there. The green area is my company, KDAB. We also contribute a lot, as you can see. And everybody can, of course, go online and submit patches if you find some bug or you want to contribute a feature, which is exactly what we did with Qt3D. We started developing it as a company and then contributed it upstream. Maybe you work for one of those companies. Qt is used almost everywhere. Any big companies use it either internally or on user-visible products. You can spot some names over there, like these names over here. Yeah, this should tell you where it's used. or should give you some ideas about where it's used. It's used in a lot of customer products, such as cars, user interfaces for them, embedded, and of course, desktop applications. Yep. So Qt basically sits in the middle between the operating system and several of its sub-frameworks that it offers. It offers something called widgets, something called Qt Quick, and of course, it also offers something called Qt3D right now. Very, very briefly, I'm telling you, with Qt, you have basically two main UI stacks, and we're going to see both somehow. One is called widgets, and that's the thing that you use to build desktop-like applications. And another one is called Qt Quick, and it's the thing that you use to build, if you want, more fluid, dynamic, touch-oriented applications. Yeah. To give you an idea of the difference between both, this is a Qt Quick application. Of course, the 3D part of it is rendered using Qt3D, but the controls and interaction, as you can see, is very touch-oriented. I got this free-floating interface, animations all over the place. Yep. So the 2D parts of it is built using this technology called Qt Quick. The 3D part is built using Qt3D. And to give you a counterexample of a widget application, this probably looks like a widget application. It's a typical thing in which you have text editors, widgets of some sort, lists, numbers, etc. Of course, you can make these much more better looking, but even in a widget application, you can have, of course, 3D content rendered using Qt3D. Yep. So just to give you an idea, you can have Qt3D in both kind of user interfaces. Doesn't matter what you're building. Just close this. Yep. Okay. All right. Now the thing is about Qt Quick is that you don't build them in C++. You build them using a declarative language using QML that I'm going to use soon enough. All right. So that's enough of introduction. Let's talk about Qt3D. That's why you're here, I hope. So what does Qt3D come from and what's its feature set? So the most stunning part about Qt3D is that it is not about 3D at all. Actually, it is also about 3D, but at its very core, what we built was a generic simulation engine, a soft real-time simulation engine that it's able to run tasks. And amongst these tasks, you can have tasks that render 3D stuff. But the idea that there are several ideas that led to this decision, and they were mostly influenced by modern game engine design, is that as soon as you have 3D graphics, you probably want some other sort of simulation also to happen at the same time. You may want physics simulation, you may want audio, you may want your domain-specific simulation to run as well. So all of this needs to be run inside some sort of engine, and what we built was this kind of engine. Yep. So the core of Qt3D is not about 3D. The core of Qt3D is about running tasks in a parallel way, and it's basically about having a very powerful threaded backend that is able to do things, run arbitrary jobs. Yep. Right now, we just have a few kind of jobs, render jobs or input jobs or stuff like that. We're already working on a physics engine based on Bullet to extend this to physics. Somebody else is working on audio. If your application deals with audio, you can build several things on the backend. And this backend is actually heavily threaded. So what you do inside Qt3D is basically you describe a scene, and the scene is rendered through a much powerful backend, scaling on all your cores and able to target even more the more modern hardware. The other part about it is how do we make this thing not tied to just what we see today? That is, today we target 3D. Fine, we can provide 3D APIs. What happens if tomorrow somebody wants to add a new set of APIs for dealing with another domain-specific simulation? We cannot foresee all the possible combinations. So we must make sure that when we design Qt3D, even our users will be able to poke in and extend this engine with custom tasks. And that's where this entity component system kicks in. So I'm going to describe that a little bit in a few slides. Was all of this necessary? Why did we go through this journey? Well, there is a reason why we went through this journey. It was this. After like 35 different customer projects in which we reinvented the plumbing of Qt3D, we decided, you know what? Writing OpenGL code by hand is very, very tedious. Yes, Qt offers a way for you to create an OpenGL window and start drawing inside of it. But you don't want really to do that. The first thing you're going to do is abstract somehow from OpenGL and start, for instance, encapsulating what is a C API into a C++ API, something more object-oriented. Of course, this means that you're inventing some sort of engine. And after we did the work many, many more times, we decided this stuff is better be somewhere centralized so all our users can use it. So why not just using an off-the-shelf product? There are 3D engines in the market. Why reinventing it? Well, the thing is, we wanted a deep integration with Qt. We did not want people to marshal data into a 3D engine and marshal data out of 3D engine. Typical 3D engines tend to be in control of everything inside your application because they're so powerful. We did not want that. We want something just specific for this kind of stuff. So you can easily integrate it inside your Qt application. Also, modern game engines tend to be quite heavy on resource. Instead, we want to target a whole array of things, including mobile if you want. Yep. So for that, we wanted something streamlined. And the ultimate idea is that for you to basically focus on innovation and new tasks rather than plumbing. Does it make sense? Yeah. So what are possible use cases for all of this? We don't know yet. I can tell you what we use Qt3D for. We use Qt3D for automotive. We use Qt3D in scientific and medical visualization. We use them for interactive manuals. So an operator operating a machine can have a 3D visualization of what he needs to do on that machine and tell, look, you need to move this piece, you need to turn this lever, and so on. That's much, much better visually rather than having this stuff on some printed manual, which has been probably photocopied 1,000 times, and then people cannot even read it. Yep. So I told you about this entity component system. What is it all about? Because I'm going to give you an example in a minute, but I need you to understand this first, so I need to explain this entity component system. What is it all about? Entity component system, how many of you have heard of this term before? How many of you have used an entity component system? Okay, just some of you. Good. So an entity component system, if you want, is a design pattern. It's a way to solve a problem of adding features inside a system and scaling linearly with the number of features. What do I mean by that? Suppose I want to simulate, I want to model, actually, that game, Space Invaders. Yeah. So this is a game. It has many things going on. Well, that's the Futurama version of the game, if you want. It has many things going on inside this game, right? You've got several things. You got the invaders, you got the cannon, you got the blockades, you got laser beams that have been shot up and down. Yep. Some of these objects have some different features. For instance, the invaders and the cannon can move around the scene, while the blockades are still. Some of these objects emit sounds. Some of those don't emit sound. Some of these objects can collide with other objects. For instance, laser beams can collide with the invaders, with the blockades, and with the cannon, and also with the ground, because if they hit the ground, they will miss, and so on. Yep, you got many features that you want to model inside this system. So traditionally, this system has been modeled using inheritance and building an inheritance tree, which would probably look something like that. You start from some base class inside your system called object. Then you make a renderable object, which is something that you can render, because perhaps you have things that you don't render in the system. Then amongst the renderable objects, you got the ones that can move, the movable ones, and the ones that you cannot move, the stationary ones. And amongst the stationary ones, we got like the blockade and the ground. And amongst the ones that can move, you got the player and the NPCs. And amongst the NPCs, you got the space invaders and the flying saucer that sometimes appears. Yep. Makes sense? Well, that's how things are still taught in universities, by the way. Yeah, to mold this system like that. Problem. I want to add a sound. Where do I add sound effects inside the system? Notice that we have different things that may emit sound. For instance, the Space Invaders may emit sound, and also the blockade may emit a sound when hit by a bullet. So where do I add the sound? Well, of course, I add it in the base class. And now I want to add physics, and now I want to add AI, and now I want to add something else, so that base class becomes something like that. It becomes the usual God object or the God class that can do everything. Right, this does not scale. This is not a good idea, because it means that in every subclass you're going to pay for a lot of functionality that you're potentially not using. Is multiple inheritance a good approach for this? Well, maybe it is, maybe it's not. People don't like multiple inheritance because you start introducing diamonds inside your hierarchies. This, especially in C++, is a problem. So people don't like that. Perhaps you may have mixins. So you have like a base hierarchy and then mixins that you just attach. But what is a mixin? So what you classify as a mixin and what you classify as your base hierarchy? It just becomes a convoluted mess. You don't know why something has been split out or why something has not. Yep. So this does not scale. And if you want the traditional solution to all of this, is not by using inheritance, of course, it's by using, composition. You don't inherit from classes. You have a scene object which aggregates a few components. Yep. However, traditional composition still has a problem. Actually, it has two problems. The first problem is that the number of components that you can attach to a specific object in your scene is baked in when you build this object. When you define this class, you define it in a way that it can have exactly at most one sound emitter, at most one renderable, at most one collidable component, and so on. What happens if tomorrow you figure out you need something else? You need to go there and change this inside you need to change that class definition, basically. And if that class definition is inside somebody else's library, you cannot do that. Right? This, again, does not scale. The second problem with doing this is that several of these components will need to know about each other. For instance, the animating needs to know if the element is movable. Yeah, so those components are not truly independent. They still have interdependencies. And in practice, this means that the system, when built, is a total nightmare of things that know or make assumptions about each other. So in Q3D, we did not go for this. We went for a total, or if you want, for this other approach, which is still based on composition, but it's done in another way. It's called, again, an empty component system. And it works this way. Inside your scene, you've got things called entities, which are literally called entities. That's the classes in Q3D. An entity can aggregate more components. And a component is more or less a bag of data. So for instance, a component is data for the physical simulation, or transformation, or a shape, or a material, or stuff like that. Those are just bags of data that describe what your entity looks like, what it can do. Separate from these bags of data, you got things that we call aspects that go on your scene, figure out what a certain element can do, and do stuff with it. For instance, if I got an entity which has a shape, then I can use it to render it. So at runtime, I figure out I've got an entity which has a component of type shape. Let me render that entity, because I know that I can do that. Yep. At runtime, I go on my scene and figure out what I can do with my entities. That's how things work in Q3D. So the shape of these is totally dynamic. You can build this thing at runtime. You can change stuff at runtime if you want. You can add more components if you want to add the physics simulation onto something. You can remove components if something does not need that particular aspect anymore. Does it make sense? Yep, OK. So, OK, there's a wrap-up of what just said. I'm just going to skip on the slide and give you an example of all of this. And of course, this example will show a 3D donut, because everybody loves donuts. Oh gosh, where did creator go? Oh, here, OK. Can you read that even in the back? OK, I can zoom in if you want. So I'm going to give you a very quick example of a scene built using Q3D. This is a C++ example. As you can see, it's quite verbose. I'm going to trim this down in the next slide. But I won't really to be as verbose as I can in the first step. So what I do here is build a simple scene which displays just one donut. How do I do that? The first thing I'm going to build over there, here, is an entity that I'm just going to use as the root of my scene, and doesn't do anything. I'm just using it to create actually the scene. Then I create the donut. The donut is another entity which is in the scene. That's why I'm passing the scene as a parameter of the constructor. Then in Qt3D, as I told you, in order to see something, I need to basically attach components to that entity. And in particular, the rendering aspect of Qt3D is going to look for geometry to render and a material to render the geometry with. Yeah. And that's exactly what all the other lines of code are doing in a very verbose way. Over here, I'm creating this torus mesh, which is a component. As you can expect, it's a component which holds the geometry, which looks like a torus. I can set a few properties on it, like radius, etc. And then what I do is add that mesh as a component on the donut. I'm creating the composition at runtime. Yep. Of course, if I do that and display my scene, I would just see a perfectly black torus. I also need to add the material. And in this case, this material is something quite fancy. It's a material which does normal, diffuse, and specular mapping, if you're familiar with these terms. Yep, it's a textured material, which looks cool. And to build this material, so this material, again, is another component. But I need to build it by loading a few texture files from disk, which is all these other lines are doing. And over here, line 54, so let me scroll down a little bit. Over here, what I'm doing is adding the material, again, as another component on the donut. So my donut is now made up of two components, the mesh and the material, and now can be rendered on the screen. Yep. There's also a third component, a transformation. I don't want my donut to sit on the x, y plane. I want to rotate it around the x-axis by 90 degrees. So I create a transformation component and add that component to onto the donut, so that now the donut sits on the XZ plane. Yeah, quite fancy, right? Yeah, so that's how I build my scene, basically. Well, that's how I build a very simple scene, which shows one donut. Let me hope this works. Yay. Yeah, very, very fancy. Of course, that's not all of it. There is something else, which is, to see this thing, I also need a camera pointing at the donut. So that's what the other code is doing. It's a little bit of boilerplate if you want. So to see something, I actually need something else. In particular, I need a window, a Qt3D window, to visualize 3D content. Yep. And what I'm doing on this window is basically set the scene inside of it, the scene that I just built above with all those entities and components. Yep. I also need a camera. I also need a camera controller to move the camera. It's very straightforward if you think about it. Okay? Also, something else which is I just added for the fun is a point light, because I want to see something in the scene. Yep. But all of this is really, don't focus too much about this. The real magic happens above here. This is how you build scenes. Everything else is just a little bit of boilerplate, which I'm going to get rid of in the next slide. Yes? So you see a lot of new, yes. And what else do you see? Right. Yes, you don't see any delete. But, this may scare people out when, of course, you're using Qt. So in Qt, there is a mechanism I'm going to explain in a minute, which is a mechanism to automatically manage memory. So this is effectively an object that could possibly be leaked. But this second object over here, the donut, as you can see, I passed scene in as a parameter. This, what it does is parenting the donut object to the scene object in a way that when you delete the scene, the donut is going to be deleted as well. And what you do is basically build a tree of objects in a way that when you delete the root of the tree, the entire tree gets automatically deleted. Does that make sense? Yeah, okay, so basically this is giving ownership of this donut object to the scene object. So this is now owned, and it's fine. It's fine like that. For various reasons in Qt, we cannot use too many smart pointers. And I've already told you that Qt was out before the first C++ standard was out. Yeah, and that is how it still has an impact today, unfortunately. We cannot change things too much, and we still need to require to compile on very old compilers. That's the reason, ultimately. So what happens here is that all the objects I'm going to new inside this function are actually eventually getting parented to other objects. So all I need really to remember to delete is the root, which is the scene object, which I'm actually returning out of this function. Yep. And the way I'm using it is over here. I'm creating the scene and setting it into the window, and then now the window, which is an object created on the stack, has ownership on the scene. So when I delete this window object, the scene is going also to get destroyed. That's the way it works. So that's how we don't leak anything inside this construct. I'm going to go back on this in a second. Okay? Does it make sense to everybody? Yeah? Okay. So as I told you, what we do is basically we create an entity, and in a more complex scene, I'm going to create one entity for each object in my scene, and I create components and attach them to entities, and then use them to show something. Yeah. Each component does something different. We got components for geometries, components for materials, components for lights, components for transformations, components for everything. Yeah. Just bags of data that you can attach to things. So as I told you, there was some boilerplate. That code was very verbose, very hard to read. So I'm going to show you a slightly different version of the same code. Oops, I opened the wrong thing. Still works? Yeah. So that's the same thing. Oops, sorry. Same thing as before. But this time written in QML. QML is if you want, is a declarative language that comes with Qt. The purpose of it is to avoid all the boilerplate. So you can almost read this, can you? It's, there is an entity, which I call donut, and this entity has components. A torus mesh with those properties, a material with those properties, a transformation with that property. It's very, very easy to read and easy on the eyes when you write code like this rather than C++. I don't know if you agree, perhaps you don't, fine. You also have, there's still C++ over there, right, if you prefer to doing things in C++. So you can choose your own version. If you prefer to do things at a higher level, you can do them. And that's why basically Qt3D provides both a C++ API and a QML API. So what I'm doing right there over here is exactly what I've been doing in C++, except that you don't see any new operator. You don't see the parenting, except that since this thing is inside that thing, then it means it's parented. Since I'm creating the mesh into the entity, that means there is a parent set implicitly. So when I delete the entity, the torus mesh is going to be deleted as well, and so on. It's a nice way to create descriptions of things at a very, very high level. Yep. And I do exactly the same things as before. So in order to see that entity, I need a mesh, I need a material, I need a transformation. OK? Yes, sorry. Yeah, yes, so of course you can add things at runtime, yes. This is a very simple example, so I'm not doing it right here. OK, in C++, that's easy, right? You just do things. In QML, you can also do the same. You got many, many options to do that. I don't have time right now to do like a course on QML itself as this programming language, but yes, worst case scenario, you can write JavaScript code in there that creates objects. Worst case scenario. Best case scenario, you got objects that you need to create on demand, for instance, from a model of data. So you got many instances of objects that you want to create based on some data in some vector or something like that. You can do that in QML. So you can do everything. Okay.
Similar question, actually.
Yes.
With, using things differently at runtime. Where does assets part come from? Is that something we can declare outside of loading in this file?
Yes, yes. That's something I just had to find these things on my computer. You can specify a relative path, you can specify an absolute path. That's a small trick to make this stuff work.
Is it declared in this file or outside?
It's actually declared outside this file. It's actually declared in C++. That's something I'm injecting in QML like that. It's because we want to share these assets amongst many, many projects, so we put them in one place, and then that's how the projects find it out. But anyhow, so that's another thing. Okay. That's another QML thing. That's not the point here. The point here is how to build scenes. Yep. So very, very, very easy and very, very straightforward. Okay, so that's of course just a building block to build something much more complex. So as I just told you, in Q3D you can have both. You can have C++ APIs, you can have QML APIs, and they're basically named the very same way. So if you're using C++, you're going to use classes which are called like Q3D core node, Q3D core entity, etc. In QML, we decided to give them easier names, to be easier on the eyes, so just node, entity, and so on. They don't have the Qt in front, they don't have the namespace in front. Yeah, much, much easier to reason. But you have an identical API set between the two languages. Okay, so that's most least in terms of introduction. Let me clarify a little bit about the plumbing then. I just introduced to you the entity component system. How is that implemented and realized inside Q3D? In Q3D, we got basically these three things that form our entity component system. We got something that we call a node, a Q node, which is the base class of the both entity and components. It is a QObject subclass, which means it has all the QObject features, if you're including the memory management that I was talking about before, and including many other features such as signal slot communication, event handling, and so on. And what really does is that that's the node that realizes at the front-end, back-end communication for us. Then I got an entity, which is a subclass of node, and an entity basically doesn't do anything. It's just a way to aggregate components. And then finally, I got the components, which are of different kinds. Right? I got transformation, mesh, material, and so on. Those are the things that provide information about what my entity can do. So if you want to see an inheritance diagram, looks more or less like that. I got a QObject at the root, Q node, and then entities and components. One entity can have any number of components, and a component can be shared amongst many entities. That also makes a lot of sense if you think about it. For instance, if I have the same model, the same 3D data that I want to display in different places, I can create many entities all referencing the same component. I don't need to load the same data multiple times. Okay? So how is all of that used? All of that is used behind the scenes. You don't see it. We have got behind the scenes something that we call an aspect engine. And that engine basically runs on all over the scene, extracts data out, and looks for components attached to your entities. So inside the engine, you basically register something that we call aspects. And for instance, the render aspect over there is something that goes on your scene and tries to figure out what are your entities which have transformations, material, and 3D data attached to them. The input aspect is something that goes around, tries to find which entities have handlers for mouse or keyboard or controllers. Yep. Those are the things that basically realize one vertical slice of behavior inside your complex application. Okay? And yeah, these things don't have an API. You don't program them. They just do what you tell them to do via the components. Okay? So what we do in Q3D is we forget about the system. We just provide data in forms of components attached to entities. So we build the scene. The system will take care of everything else. We don't need to do anything else to manage that. OK. So that's an overview of this entity component system. Let me tell you a little bit about how we draw things in Q3D. So the way Q3D draw stuff is basically by building a scene. A scene is just a collection of elements inside of it, but it's important that it basically has the shape of a tree. You start with a root entity, and then you parent entities to this root entity, and you can even parent entities to other entities and so on. Yeah, that's a description of the scene for Qt3D. So your entities will basically describe what takes part of the scene, what takes part in the simulation. And you attach to each entity transformations, materials, and so on, as a framework component. By the way, if you're familiar with Qt, this is exactly how all other UI technologies in Qt work, and I'm pretty sure that any other Qt UI technology has something similar to this, a concept in which you parent things to other things together. Yep. Finally, you provide a camera of some sort to tell the system, okay, you need to render the scene from this point of view. So let's describe this one step at a time. The first thing is geometries. How do I create something which has a certain shape? Now, in Qt3D, you got basically a bunch of built-in shapes if you just need to visualize something like that. You can create something which is a cuboid mesh, and that creates a cuboid, or a cube. You can create something which is a sphere mesh, and it creates a sphere. Yep, those are all components that you can attach to any entity, and it will do exactly that. Oops, sorry, that's, sorry, I'll show the other example later in a second. What is that? Oh gosh, basic shapes. Where are you? Here. Please build, can please run? Yeah. Shapes that come with Qt. Okay? It's not particularly compelling, but the way these, sorry. Where is that thing? The way these shapes are built is basically by creating those elements just like the donut. You got torus, mesh, and that's a component, and then attach a transformation and a material as well. Yes?
Does it make sense to add two of the same component in one entity?
Yes and no, in the sense that you can, but I mean, it depends on the nature of the component, if it makes sense or not. For instance, a transformation, it does not make sense to have two different transformations on the same entity. You need to make up your mind. Well, how do you want to transform this thing, this way or that way? For geometry, it might make sense. I got something which is made up of two different geometries, so I want to attach two different meshes to the same entity. It really depends on that. There's nothing preventing you from doing that, from doing so. You just need to know which ones you can, which ones make sense, which ones doesn't make sense. Ultimately, it's the engine that runs on your scene that is it able to cope with that particular situation or not. So I can tell you, for instance, for transformation, it does not make sense. You must have one transformation. For render and for geometries, it does. For materials, it does not. Yeah, right. Okay, that's it. Okay? So there is nothing special here, basically. You can create these sort of components and attach them to your entities, and they will represent various geometric shapes. Yeah. Of course, this is very limited. There are only, like, I think 10 inside Qt3D. How about custom shapes? How about data that comes from a 3D modeling tool? Well, of course, you got also something for that. There is an element, there is a component called mesh, which is able to load any sort of 3D file from disk. Yep. So aiming something more complex, something that is exported out of Blender or Maya or AutoCAD or whatever you want. Oops. Yep. So for instance, this toy plane, this rotating toy plane, is realized, sorry, like that. I got an entity, and amongst its components, I got a mesh component, which loads that toy plane OBJ. I got a fungal material, which is just green, and I got a transformation. And this transformation actually has an animation running on it so that the model rotates. Very, very simple, very, very high level. I don't want to deal with the plumbing which is behind this stuff, which is mind-blowing. Yes?
What kind of input, what format input?
For the mesh element, so we're using Assimp under the hood, which is an asset importer library which supports lots of things. Some of the formats allow you to bake more than one mesh, in which case you can use a property of mesh to figure out which one you want to load. As some other formats actually bake an entire scene in the form of multiple meshes and materials as well. And for that, you can use another thing which is called a scene loader, which basically loads an entire subtree, will create entities and materials as it goes over your format. So, yeah, for instance, I think DAE, that format can load the entire things. It really depends on the individual format, but we're using Assimp under the hood. So whatever that's provided by that, and that's like 20, 30 different formats we can load. Okay. I don't know if you're happy with that answer or not. Okay, good. Good, okay. So in this case, it's just OBJ, a very good old wavefront format. Okay, so this is how we load geometries. There's a third use case for this stuff, which is how about I don't know my geometry data in advance. How about I create geometry data as I go inside my application? For instance, I pull data out of the database. I want to create geometry out of it. Well, there is an API for that. Unfortunately, I don't have time right now to go into much detail on that particular API, but basically it works like this. You can create geometry by using a geometry element. This geometry element holds a collection of buffers, which are just buffers of memory, and attributes. If you did a little bit of OpenGL or direct 3D programming, an attribute is a way to describe what's inside a buffer. So for instance, I can have a buffer holding positions for my vertices. That's just a block of data. And my attributes tell me, look inside this buffer and interpret the data as triplet of floats. Yep, because each triplet of float is the position of one vertex. Yeah, I can feed this data into the system by using something which is called a geometry renderer. This is the actual component that you're going to use. So you got a component which uses a geometry which is made up of buffers and attributes. Yep, and you can create all this data at runtime as you go. So it does not need to be baked inside some file that you load. So I don't have really much time to go through that. I'm just going to show you a very simple example of this thing in action. So what I got over here is a 3D scene with just a plane. And what I got over here is an area in which I can scribble. And what this example is doing is turning my horrible drawing into that thick snake line over there. This is actually 3D. This is not some, I mean, you can see it's 3D, right? The actual line is slightly above the ground. I don't know if you can see that. Yep. So this is all based on the fact that I can pass the data from that scribble line into buffers and then have Q3D render it. So the data does not need to be baked into a file. Okay? Right. So you got all the flexibility you want. You can either load stuff from file or have one of the predefined mesh if you just need to show a sphere or a cube, or generate the data as you go. Transformations, just a few words on that. Again, I don't have time to give you a crash course into 4x4 matrix manipulation. I hope you trust me when I tell you you can define most of the interesting transformations in 3D scene by using a 4x4 matrix. So how we transform things around, we already encountered one guy, which was the transform guy. Let me close this. Where were you? Here. We already encountered this guy. Yep. This is a guy that encodes a transformation. However, in 3D scenes, that's not enough. In 3D scenes, we have several transformations we need to specify. In particular, inside any 3D application, you will need to deal with with these kind of transformations. You will need to deal with at least 5 different transformations, bringing your data from your geometry all the way down onto the window. And the way we go from there to there is basically by applying different 4x4 matrices. So we go from our model into world space by applying one transformation matrix, which is called the model matrix. From the world space to camera space by applying another matrix, which is called the eye matrix, or the camera matrix. Then we go in projection space by applying yet another matrix, the projection matrix. Then we go into this other thing called the NDC, or normalized device coordinates. And then we go finally into positions on the window. How do we specify all these matrices inside Q3D? So the very first one that goes from model to world is specified using that guy, Q transform or transform. This is a very simple class that wraps a 4x4 matrix. However, it also has lots of convenience over it. So you don't need to actually build this matrix. It can do it for you. So you can build a Q transform and tell it set a translation along with the x-axis by 20. This will ultimately boil down to a matrix, but you don't need to build it yourself. It also has lots of convenience in terms of functions, like rotate this transformation around a point in space, which is slightly tricky. It requires you to do something fancy with the quaternions. You don't need to deal with the math yourself. Yep. So this is the way we can transform it. We can take any geometry and move it inside our scene, inside our 3D space. Now, transformations actually are slightly more tricky than that because they nest together. If I got an entity which is a child of another entity, the child lives in the frame of reference of the parent, which basically means the transformations get composed together. So if I create an entity like that and attach a transformation like that to the entity, and then I create another entity and parenting it, and I specify another transformation for the child, then the two transformations actually combine together. Yeah, which again makes sense most of the time. You want children to be transformed after their parents. Yeah. Notice, however, that the transformation themselves are not parented amongst, so this transformation is not parented to that transformation. It's the entities which have parent-child relationship. Slightly tricky, but yeah, you can understand why is that. Yep. And in QML, it's exactly the same thing. So I got an entity which has a transformation component and a child entity. So this entity is a child of that one, and this entity also has another transformation component, and these two transformations compose together. Yeah, so the effective transformation of this guy would be the composition of this and that. Yeah, actually applied first that and then that, get an order. Okay, so that's how we build some of those. And that's how we basically go from model space to world space. How about the remainder of transformations? How do we go from world space to camera, projection, normalized, and viewport? So camera and projection are actually handled by yet another different component called a camera. A camera, it's something that defines basically the point of view of the user onto the scene. It's something that has a few properties, such as position, up vector, view center. This defines where the camera is in space and what it's looking at. Yep. You can need to add one of these inside your scene to figure out, OK, this is where I'm looking at right now. Yep. The projection is controlled by yet another component, which is called a camera lens. Typically, you want to keep these two things separated, because you may want to change the kind of projection you have without moving the camera anyway. That's why they're logically two different things. So for instance, you may want to switch from a perspective projection to an orthographic projection. Yep. And you need to change just this lens component, not the camera. Make sense? Yep, so all of it. In practice, if you're into OpenGL, this stuff consists of a bunch of uniforms that get passed into your shaders. How many of you know GLCell or know shading code in general? OK, some of you do. Good. Under the hood, this is the stuff that actually gets executed by OpenGL. And basically, this stuff is something executed inside something called a vertex shader. And I'm about to fall down here. I hope I won't. The matrices that we define are basically passed inside OpenGL so that it's able to transform our vertices accordingly. This is all automatic done for you by the engine. Yep. So let me give you an example of these transformations inside a very fancy example, which is a small solar system. Yep. So in this example, I'm using a few spheres. And of course, I'm transforming each sphere in a way that rotates around the sun. Yeah. However, one of these spheres has a small moon. It's not a moon, a space station, or whatever. Actually, I plan to texture that thing like the Dexter. Yep. So the transformation of the small moon is relative to its parent, which is the green sphere, which in turn is relative to the entire scene. Right? So the small moon, of course, as you can see, follows the big the big green planet around the scene. Yep. So how do I achieve that? Well, it's very simple. Gosh, I always forget where is that. Yeah, here we go. How do I achieve that? I've got an entity, which is my sun. It has a few components on it. Okay? That's my sun. Then, as a child of this, of the sun, I got something, another entity, which I, for convenience, call an orbiting body. And this guy is my red planet. Okay? Now, if I go inside this and see the definition of this, it's actually an entity with a few components set on it. A mesh, a material, a transformation, and so on. But I don't want to repeat all that inside my main file, so I just show this stuff hidden in some file. And I can just use orbiting body, and I'm using some high-level properties such as the orbital radius and the phase and the period to calculate the effective transformation for this body. Yeah. And then I got the green planet, and the green planet has also as a child body. Yeah. So these transformations of this guy and that guy will nest together. Yeah. And this body will orbit around that body, which will orbit around the parent, which is the sun. Does it make sense? Yeah, it's all automatic for you. So again, this is how it looks like in the end. What's more, there is a camera in the scene, right? It's looking at the solar system. It's placed somewhere in the scene looking at the sun. But I can also make the camera look at something else. So that's the camera in the scene, that camera object. It has a position, it has a view center. Does it make sense? Yeah, so it's set somewhere, it's looking at something else. And inside this scene, I got some handling of the camera itself. When I click on a planet, the camera zooms on that planet and starts tracking it. Yeah. Or it goes back like that. The way I do so is basically by linking these properties of the camera to the position of a certain body. Yeah, and I just do that inside these on-click handlers. I really don't have time to explain the plumbing of this, but trust me, it's just a matter of changing these properties on the camera when something else changes. Yes? I'm sorry, the interaction handler? Kind of. In Q3D, we got specialized stuff, of course, because, for instance, you want to figure out when you click on that planet, which is a 3D object, you need that planet to tell you, hey, I've been clicked on. So that thing is basically encoded inside Q3D. We have something which is called a picking mechanism that allows you to pick objects inside the 3D scene and to do stuff in reaction to that. That's the Q3D specific part. Of course, that's then shared amongst the other stuff inside the Qt framework. So there is a 3D specific part, which is figuring out what you clicked on, basically. Yeah. Then how do you implement picking is another problem. In this case, it's actually using raycast picking. So a ray is projected from the camera into the scene and finding the first collision, which happens to be a planet, usually, or the sun. Yep, OK. Right, so that's about transformations. What time is it? Okay, still time to tell you a little bit about materials. So I know how to add geometries in the scene, how to position them using transformations, and how to place the camera as well. How about materials? How can I make my elements look nice? So there is a lot to say about materials. Again, I'm just give you a very brief introduction of what you can do with them. So the good news is that out of the box inside Q3D, you've got inside Q3D, you've got lots of materials for you that are just like standard rendering algorithms, if you prefer. You've got Fong and a few variations of it, such as one that uses a diffuse map, one that uses a diffuse and a specular map, one that uses a diffuse, a specular, and a normal map, and I think also one for the reflection exponent. We've got a material that uses the Gooch shading algorithm. We also now got PBR materials, if you're into PBR rendering. So you can do lots of things with these materials, and they just work. You just attach them so you just attach them as components. Why I always open the wrong file? Okay, and they just do the right thing. So in this case, for instance, I got, again, my donut, an entity, which has 3 components, a mesh, a normal diffuse specular map material, so something that you will use 3 textures, and a transformation. Yep, and this is a built-in one. I did not write it. I just need to provide the texture files, so those PNG images. And when I run this, it looks like that. Of course, it's professional. The reason it's professional is because the paths of these textures are actually, they come from somewhere else. They come from this string property that I can change inside my runtime application. So I can open a menu and change the coding. Yep. Just switching the texture files that the material is using. Very, very simple. Right? So that's, again, out of the box. What if I want to write my own material because I want to do something slightly different or something customized, or I'm trying out yet another thing? Of course you can do that. So there is a component which is called material. I'm just showing you the QML API right now because in C++ this is extremely verbose. A material has an effect inside of it. An effect has an array of techniques, and each technique specifies what's going to happen when you want to implement that particular material. It ultimately boils down to providing some shaders. Right? So you can write your own custom OpenGL shaders and render that material with those shaders. What's up with all the rest? Why there is so much stuff in the middle? So why does a material have an effect? And why does an effect have techniques? And what's the other stuff? Well, there are a few things going on. Of course, this is one of the most trickiest areas in OpenGL and 3D graphics in general. The first thing is going on is, for a given effect, you can provide multiple techniques to be realized, for instance, by different OpenGL versions. So I can provide with a very fancy modern technique, but that requires OpenGL 3.2, or a fallback option, which requires just only OpenGL 2. Yeah, I can have like a more advanced effect and slightly less advanced effect, and I can implement those using different techniques inside the same effect. Yeah, so that's that step there. Okay. Also, at runtime, I can decide which technique to use by filtering them out using these kind of name value keys. So I can just switch between techniques by saying, now render using the techniques which have those certain keys inside of them. Okay, that's the first thing. The second thing is that you may want to share the same effect amongst different materials, but just change the effect a little bit. For instance, I want to use the same Fong material amongst many different entities, but each one should have a slightly different diffuse color. So the color is just something that is unique per material, but everything else is shared. The shaders are the same. Literally, everything else is the same. So what you can do is build different materials using the same effect and just change one parameter of the effect. Yeah? So you don't build many objects. You don't build many shaders. You just build the effect once, and you build different materials out of the same effect. And finally, there is this thing called render passes in case your technique requires more than one render pass over the scene. There are more complicated techniques that allow you, that force you to basically do several passes over the same geometry to visualize a result on the screen. So we support that too. Yes?
When you change the property on a component,
Yeah.
then does that somehow fall back into the engine so it knows to redraw?
Yes.
Does the engine have to do a full relayout every time something changes?
No, so what happens is that when you change a property on the component will call back into the engine and tell the engine, hey, I've been changed. Please synchronize with me and redraw the scene. So that's what in practice happens.
The engine is smart enough to realize it might need to do nothing or might need something.
It really depends on the nature of the change, whether something like that may cause a complete redraw or not. Again, or what actually happens. If you change a transformation value, that's just a matrix somewhere that needs to be changed. If you change a mesh, if you tell a mesh, load this other file now, that causes massive changes at the engine. It causes several deallocations of the old data, loading the new data from another file. And perhaps it needs to unload that file first, and so on. That's another thing. Then whether that causes a redraw, that's another story. So the engine still has to reload the mesh, but then perhaps decides, but that's outside the camera frustum. I don't need to redraw the scene. So there is a lot of optimizations in place, and we're still working on so many more optimizations that you can do with this stuff, yes. It depends on the nature of the change, really. There is no yes and no answer. It really depends, I'm sorry. Okay, right. So again, this is just to give you an idea of kind of materials that you can build. So let me give you a small example. This is an entity, which is a sphere, and which is using a custom material, which boils down to custom shader code. So when I run this, I see this very fancy sphere, which looks kind of fancy, right? It's strange, kind of strange. It's simply encoding the vertex position in world space as colors. So these parts over here are big in the Z space. This part over there are big in the X space. The parts over there are big in the Y space. And if you encode X as red, Y as green, and Z as blue, you get that. How do I do that? Well, custom shaders. But if you are able to write shaders, you can write your own material that does custom crazy stuff. Of course I can. I think they're just like 3 lines of code. Well, more or less. So that's the vertex shader. Let me see. Oh, bad idea. Perhaps like that. OK. Bad idea, nonetheless. Sorry. OK, that's the vertex shader. Yeah, it just takes the vertices in some local space, plus normals that I'm not even going to use. These must have been copy and pasted so many times. Yeah, because I'm not using those information, and I output some world position to the fragment shader. What I'm doing here is actually multiplying the model matrix by the vertex position. So I go from local to world space. Yep. And this guy goes down into the rasterizer. And then I'm also figuring out what's my position into pre-normalized coordinates in clip space by multiplying the model view projection matrix with, again, the position. And this gives me the coordinates in clip space. Is that fine? Can I switch to the fragment? Yes? No? OK. And, oh, sorry. And the fragment, well, just takes the world position and says, no, this is now a color. So encodes the world position information as a color and actually runs an absolute over it. OK, yeah, yes, I know it's ridiculously simple, but the point is that you can write your custom shaders. It's not that you can only use Fong because we designed this thing with Fong in mind, and that's it. OK, so custom materials. And custom varying materials. Because the thing is this, typically you will have many, many materials that do exactly the same with a small change into them. This small change is typically encoded inside your shaders by something that we call uniforms. A uniform is basically an input in the shader, which is constant for an entry draw call. So what you can do inside Q3D is having some guys called parameters that are able to change what a shader does just for that particular draw, and not without having multiple copies of the same shader. So that's a more convoluted example. I'm using a material, which is using an effect, and inside this material, I'm also specifying a few parameters for the effect. Actually, parameters, you can specify them all the way down. You can specify parameters on the material, on the effect, on the techniques, and on the render process if you need to. Yeah, and these things cascade as expected, more or less. Okay, so suppose I got a material which is Fong, and I just want to change the diffuse color, but it's the same material for all the entities in my scene. I can create one effect, many materials, and just change a parameter in the material sharing the effect. That's the whole point. To show you this, is this building? Yeah. Yeah, so same sphere as before, now going dark if I want to. How is this implemented? I got basically the same material as before, but this time this material has a parameter, which I call darkness. I got an animation of that darkness property, sorry, on that value property of the parameter, making it go from 0 to 1 and 1 to 0. Yep. And this guy is actually used inside the shaders. Inside my shader, I can pick that guy from that uniform and then apply it, like multiply it, and so the color gets darkened. So I can modify my shaders using parameters inside materials. Does this make sense? Right. So I'm running almost out of time. Let me tell you just very, very quickly about texturing lights. Of course, you can specify textures, because textures are fundamental to give your scenes some degree of realism. The way this works is pretty much just the same. You specify textures as parameters of your materials, and they get down into your shaders as textures. Yep. Some materials expect you to provide textures. For instance, the Fungal materials that I've shown before already have hooks in place for you to provide textures as paths on disk or paths to download from the network. If you're writing your own, what you need basically to do, so I'm just skipping a couple of slides, is provide hooks that give you a texture back. So in Q3D, there is this guy called an abstract texture that is a generalization of textures. And you create these guys by using a texture loader that is able to load the texture from a file, from memory, etc. Yep. And then you put them into the engine, as I told you, as parameters of the material. So I create a parameter whose value is a texture 2D, which has all the settings of a texture, linear sampling, bilinear sampling actually, as mid-maps, as also anisotropy filtering, and is loaded for using that Bricks PNG file. Yes?
You very briefly mentioned memory, and it's loaded by video.
Yes. We don't have yet something easy to do that. In Qt, there is a framework for video. It's called Qt Multimedia. We're just missing a ready-made element that allows you to basically give a video file and load the video file as images in texture. We're missing that building block, I'm honest with you right now. But if you have the video frame decoded somewhere in CPU memory, you can upload that into a texture. Ideally, you don't want to do that. Ideally, you want to code that video frame in GPU memory and have the driver give you that texture image as an ID, so that you don't need to transfer it back and forth amongst the GPU, the CPU, the GPU again. But you can totally do that, yes. Okay. All right, so we also have textures. Again, I don't have time to give all of that, but trust me, you can build custom materials, custom fancy materials with multiple textures, such as this nice reflecting earth which has 3 or 4 texture layers, one on top of each other. It has a Gaussian layer that you can see is reflective. It's reflecting the light of the sun, a ground layer, and a cloud layer on top of that. That's 3 textures in one go. Yep. And finally, lights. Of course, we wouldn't see anything inside a scene if we don't have a light source. So 2 options of this. Either you encode your own lighting algorithm, which is one story. The other option is, in Q3D, we got a bunch of lights that just work with the built-in materials. Lights are basically components that you can attach, again, to anything and make that something be a light emitter. And in Q3D, we got these 3 guys. We got a directional light, we got a spotlight, of course, and we got a point light. Yep. So we can use them. We can add these components into a scene and see the scene lit from a certain point of view. Oh, what? Sorry, something bad is happening. Yeah. So now where is X lights? Here. Good. Is this thing working? Where are my lights? Okay, over here. Bingo. Yeah. So this is so 2 spheres on the ground lit by a directional light, a point light, and a spotlight. I don't know if you can see that on the projector. Yep. Inside the scene, how do I encode this? Well, I simply make an entity which has a point light component over it. This makes this entity a light emitter. Yep. Note that the entity itself is not visible because it does not have a material. Does not have a material in it. Does not have 3D geometry on it. You could attach it to make like a lamp shape that also casts light into the scene, but those 2 things are independent and orthogonal. Yep. Similarly, I've got a spotlight over here, which is blue and has all various parameters for spotlights. Okay. So that's the idea. Yes.
Is there also an ambient light?
So the ambient light, you can specify, usually you specify the ambient light into the material itself. So when you use a Fungal material, so that's the ambient diffuse specular model, you can specify an ambient right there. I don't know if there's like a generic way of doing that everywhere, usually because you usually tune it per material or per entity because it's still Fungal, it's not something too accurate. So it's taken into consideration. It's just not a global setting. It's not something that you just add it to the scene and it goes everywhere. But that's a good suggestion, actually. We should probably implement something like that. Or having like a default fallback if you don't say otherwise. I don't know.
It would make it easy to get started if you have no idea where your lights are. If you're looking at the scene, the camera's pointing towards any object at all.
Yeah.
Line up something.
Yeah. So. Actually, if you're using the convenience, we always add a light if you don't say otherwise. But that's just if you're using the convenience because you want to see something and you don't want to spend time figuring out why I don't see anything. Yeah, because you need to add a light. But otherwise, you need to add lights into your scene. Okay? So I'm almost finished with this part. Do you have any other questions before I jump to almost to the conclusions? I want to give you another couple of ideas. So, yes? Sorry? Before I go to that topic, thank you. Before I start talking about how to render in different ways, so this is how we build a scene. Of course, it is extremely simplistic if you want, but it's really the building blocks. You can build on this. You can create very complex 3D scenes, such as the nice car that I've shown you at the beginning. So let me actually go. Sorry, where did I go? No, wrong. Okay. Let me actually talk about this a little bit, which is, yes? Logic? So there is something that is a logical component. It's something that gets triggered at every frame, basically. So you can do that. perhaps that's fine with you. If you need something more complex, that is something that runs on the back end, then let's catch up later, because that's an entirely set of different APIs. For something simple, there is something which is called literally logic, and that's something that offers you a function that gets called at every frame. So if you have that hooked up, you can go together with the simulation, basically. Have your entity think or calculate things and change every frame. Okay. So to conclude, or not to conclude, but just to give you another idea, this is how you build the scene. How about controlling how I render the scene? Because the thing is this. Usually 3D engines don't allow you to control exactly what is rendered and how it's rendered. They just tell you, yeah, I render everything which is in the scene. I don't care. I don't let you give that degree of control. In Qt3D, we wanted to give users that degree of control. And for that, we basically built something that we call a frame graph, which is a data-driven description of how the rendering engine should render the scene. Now, this kind of control is fundamental to do any sort of things, such as post-processing effects or rendering shadows or employing something called deferred rendering and so on. If you're doing something slightly more fancy, you basically need to get in charge of the rendering algorithm and tell the engine, please follow me and do this first, do that later, and so on. Yep, and we want you to be able to do that. So what you're going to do inside, if you want to control that, is use one of those components called the render settings. A render settings is a component that allows you to choose how the rendering is done. And what it basically has is a property called active frame graph, which describes the frame graph of your scene. So let me explain how that works. Sorry, bad picture. Let me explain how that works. A frame graph is a tree of instructions to the renderer. In the most simple way, when you use the convenience, you see the tree looks like that. The tree it starts from viewport, which means set a viewport which matches the entire screen, clear the buffer before each frame, and use the main camera as the camera for this rendering. Yep. The way this thing is interpreted is you start from the root and you go down the tree until you hit a leaf. Once you hit a leaf, this forms something that we call a render view, which is a collection of settings to render the scene with. Yep, so the scene is going to be rendered using all these settings, and then that's what happens. The scene is rendered exactly using those settings, which is something simple that you want to do most of the time. What if I want to change this stuff? For instance, I want to draw the scene multiple times in multiple viewports. Yep, so that's my scene, but I also want to render it from different cameras in different parts of my window. How can I control all of that? Well, what I have are basically a bunch of nodes inside that tree that allow me to specify exactly that. For instance, like this. I build a tree of nodes which looks like this. It starts with something that says, I want to render to my window. Yep. Then I got a bunch of branches. And what the renderer does is following these branches, basically in depth, left, visit, and building settings. So for instance, it starts from there, goes down this branch, and hits this leaf. And that's one way, that's the first thing that the engine needs to do. So the first thing you need to do is to target the window, clear the buffers, and don't draw anything. Yep. The second thing you need to do is go through this other branch. So set the viewport to the top left of the window, select a certain camera to render the scene with, and then render. And you can add, so there is like 20, 30 different kind of nodes you can add. You can add nodes that specify which entities you want to pick up based on something we call layers. You can specify settings such as draw with depth testing or draw without depth testing or with stencil testing or without it, draw to the screen, draw to an off-screen surface. Yep, you can specify all sorts of things inside these branches. And this controls how the rendering is done. So to give you an idea of this kind of multi-viewport thing. So that's the scene rendered 5 times in different parts of the window. come on. Where's the frame graph? Here. And that's my frame graph inside the tree. The frame graph looks like this. I got something which I call render surface selector that figures out, okay, you need to render to the screen. And then there's a bunch of child nodes which basically build the tree. Yep. Each node actually has sub-children. And the render visits this tree in a depth first visit. So the first thing it's going to do is going from there to there to there, and it's going to apply this set of settings, not draw anything, but still clear the color and depth buffers. Then the second thing the engine is going to do is, yes, sorry? Oh, sorry, I thought you raised your hand, sorry. The second thing the engine is going to do is start from there, visit that viewport, and visit that camera selector. And this tells basically, draw something in that corner of the window using that camera. Since I'm not filtering out anything, actually this will draw the entire scene from the point of view of that camera. Then draw then the other branch, another viewport, another camera, and so on. You can build arbitrarily nested things in there, of course, and the engine is going to visit them all in order and assemble a frame by following all these things. So all of this will happen to produce just one frame from the engine. Yep. Does it make sense? It's a quite powerful technique, and I'm not aware of any other engine that actually offers you this degree of flexibility. Because once you start doing this, then you can go really crazy and, for instance, have this kind of post-processing or rendering to texture effects. So you can tell the engine, render something, and actually don't render it to the screen, render it into a texture. And you do that in one branch of your frame graph. Then the other branch of the frame graph, you tell the engine, please use the contents of this texture and actually draw to the screen. You can build multi-pass techniques by simply specifying each pass in a different branch of the frame graph. And okay, I got a bunch of examples over here, but let me just give you a simple one that really shows, I think, why one might want to do that. So I've got a scene with a few things around, and I think if I click on a scene, that something becomes highlighted. Yep. So the way you do that effect, and it's something that a designer may come to you and ask you to implement that for him or her, is simply, well, not simply, you render just the things that are selected, not everything, inside an off-screen texture. Then you blur that texture, and then you draw your scene normally and the texture on top. Yep. So you need to do different passes over the scene, and in one of these passes, you need to target something which is an off-screen texture, blur it in another pass, and then compose the scene, compose the textures together. Yes?
The root concept is still a scene, right? Whatever I do is still part of the same scene?
Yes.
Okay, but I could also split objects into two sets.
Yes.
To like render only like interior apart from exterior
Yes.
objects.
Yes.
Okay.
Yes, you can tag objects by something we call a layer. So you can classify, this is my internal, this is my external, and then inside the frame graph, you can tell the rendering engine, draw only the objects with these tags, which is exactly what this thing is doing, by the way. It's tagging them, but the tags change depending on whether the object is selected or not. Yep, so I got a pass in which I just draw the selected ones, in an off-screen texture, which is all green, and then I blur the texture, and then I draw on the screen. And all of these visualized. Where are you? Here, yeah. It's something kind of tricky, not so much. So that's my frame graph. It starts with something that says, I want to render to the screen. And what happens there? I got another one, which I think still targets the screen. And then I select the camera, which is my main camera. I clear everything with white. And then I draw all the objects which are tagged, I think. Yep. And I actually draw the environment which is around it. Then I know another pass over here, in which I clear the buffers, and here, this selector actually is targeting into a texture. So this thing actually renders, sorry, I should go always to the leaf. So this thing clears the buffers into an off-screen target, renders only the selected objects, and uses only the materials which are tagged like that, and uses the main camera to render it. All these settings are basically composed until we hit a leaf. Yep, and that's a second pass over the same scene. Then I got another pass in which I change the camera and I blur the thing. And blurring in OpenGL is done by basically ping-ponging between two textures, applying blur passes. So these are all subtrees in which I ping-pong and apply a horizontal blur, vertical blur, horizontal blur, vertical blur, until it actually is blurred enough, and then I compose everything together. Yep, tricky, but you got all the flexibility that you want, and especially that artists demand out of people right now when you want to implement some total custom rendering algorithm. Okay, so I'm almost running out of time. I'll just give you a brief idea of, so there's much more to be said. This is actually a condensed version of something that I give across 5 days, so please. I'm serious. There's so many things that one can tell about all this stuff. Just tell me where we are right now and where we're going to. So, of course, everything I just shown you is there, and it's available in Qt 5.8. Qt 5.9 is due to be released in 1 month, so I'm just give you an idea of what you can expect inside 5.9. Lots of goodies, such as you can use an imperative painter to paint into a texture. You can have text in 3D, both on a flat surface or actually extruded in 3D. We got LOD support for meshes. We got PBR materials. We're starting to get something like input from arbitrary controllers. We're getting especially something interesting, which are keyframe animations, because people demand to have proper support for animations, not just models that rotate around a point, but having actually baked animations and so on, and especially auto tooling. There's already some tooling existing, but we want to build a full 3D editor that allows you to drag and drop elements in the scene and build the code for you rather than you writing all this boilerplate yourself. Right? So, yeah, many things. Do you have any final questions? Yes. Okay, just go here.
Going to the do you support skinning?
So, not right now. I think skinning is planned for 5.10, which is end of this year. Yeah.
Is that something you would do in post-processing, or do you have a concept of a manipulator in the system?
It depends on what kind of manipulator you want, really. If you want.
Rotate or translate objects, so mouse picking.
Yeah, so we got mouse picking already. Picking is already implemented into the engine. And actually, also keyboard is implemented inside the engine. So if you add the small arrows inside your 3D scene, you can detect clicks on those and then do modifications of the scene based on those elements. That's already doable right now. There's no convenience if you want, but again, that's a good suggestion. By the way, yes, if you've got suggestions for this kind of stuff, please just go on the mailing list and say, wouldn't we solve a tremendous amount of time if you could just implement this inside the engine? And we can easily do that. We just don't have enough feedback from the market yet. Okay, you're welcome. Yes? Goes to the engine for? Yes, not so much. I don't have any hard numbers to give you right now, but we're able to run on pretty low-end hardware, embedded boards of some sort, as long as basically you have OpenGL, this engine runs. So that was one design goal, by the way. We want this thing to scale down as well as up, because people have, okay, this thing, and also to have an eye for power consumption, which is something always forgotten, but this engine right now runs on things such as IMX6 or similar technologies, which are quite, they're not powerful at all. Probably your mobile phone right now is much more powerful than those embedded boards, and the engine runs. Yep. Yes? Yeah. Yes. Yes, so the question was if all of this is meant to be portable. Yes, it is. it's Qt, and Qt is portable, yes, but we don't want to give you any constraint. Yeah. Yeah. Yes, so unless you write something like shaders that don't run on Android, that's another problem. Okay, yeah. But yes, in principle, this all runs everywhere. It's actually currently running on Android, iOS, Linux, Windows, Mac, Unix, and I don't remember what else has been tested so far. It's in the nature of Qt to be Qt, sorry, not Qt, to be cross-platform. Whether this means for you writing then a QML API, QML UI for an entire application, a widgets one or nothing at all, that's another decision. Okay. Yeah. Oh gosh, everybody has a question. But I think we're out of time. Yes, I see Herb over there looking at me very, very. Okay, so please go on. Yes, yes, please. Licensing. Well, I mean, this is shipped as part of Qt. As such, right now, it's under LGPL version 3, or you can buy a license from the Qt company if LGPL version 3 is not fine with you for any reason. So it's just following that model. That does not have its own model. It does not have things such as revenue share or other models that are now popular with engines. It's just part of Qt, so it follows the same Qt licensing model. Okay? Yes? At the moment, yes, but yes, so there was a mention of that, yeah, going on. We're looking, so we're already working with Vulkan, and we're keeping an eye forward on these things. As a matter of fact, we just did not port the engine to Vulkan yet, since there's been no requirement from anybody almost to do so. In principle, there is almost nothing that is actually then tied to OpenGL. It's just the shaders, if you want. That's the only thing that right now a GL cell. So yeah, you could compile them on the fly for Vulkan, but for instance, not for Metal, not for like 3D12. But in principle, it is totally possible to build multiple backends for this thing. Again, we want to be cross-platform. Right now, the best cross-platform solution is still OpenGL. So that's why we target that first. Yes?
There's a technology, I can't remember the name, you probably know it, where you share sections in the graphic between applications, which you'd be able to be a client for someone else's applications.
Yep. 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 Well, I mean, it's not as is a part of Q3D. If you're using one of those technologies, what they give you most is basically a texture handle and a way to synchronize with that. Like, okay, if you're a client of the texture, it gives you that's the handle of the texture, or multiple handles in case you need to do some kind of round robin, and a way to synchronize with the producer. So you can consume the handle as is in Security. You just need to build a texture object out of the texture handle, and then you display it. You can just use it today. Making Q3D producer, I have no idea how to do that. I'm pretty sure it is possible in principle. Again, it's a matter of building a frame graph which targets some kind of, again, off-screen memory, which is probably, again, allocated in some platform-specific way and possibly looks like a texture or very similar, so you can target it as a rendering surface. That's, I think, the most sensible thing. I'm not totally sure on that. If you want, I can do some research and come back to you. Okay. Okay, any other question? I saw lots of questions. But I also see people outside, again, very, very anxious to welcome her back in. So thank you very much.